Okay, let's get started, everybody. Welcome to this week's research seminar. I hope everybody can hear me okay? All right. So for our speaker this week, it is my great pleasure to introduce Dr. Natalie Parde, Assistant Professor, Department of Computer Science at the University of Illinois, Chicago. Dr. Parde holds a BS and MS in computer science and PhD in computer science and engineering, all from the University of North Texas. Dr. Parde has been at UIC since 2018. She is the co-director of the UIC Natural Language Processing Laboratory. Her research interests are primarily in natural language processing with emphasis in healthcare applications, multimodality, creative languages, and more recently, identification and analysis of health-related behavior. This summer, Dr. Parde and her collaborators received a huge grant from the National Science Foundation, National Science Foundation's Smart and Connected Communities Initiative for the project titled Smart and Connected Family Engagement for Equitable Early Intervention Service Design. This is a $1.17 million grant over 3 years to culturally adapt, personalize, and evaluate an electronic tool that engages early intervention families in assessing and planning interventions that improve young children's participation in valued activities. I'm glad to have her today at our colloquium to share her research work. The title of the talk today is The Doctor or Chatbot is in, towards automated support for healthcare tasks using natural language processing. Welcome again. Thanks for being here, and please take it away.
Thank you. Thank you for the introduction, and I'm very happy to be virtually visiting DePaul. I actually live very close to the university, so this is fun. So today I'm going to be talking about some of my team's work in natural language processing that intersects with the healthcare space, where we are developing techniques to support wellness through analysis of spoken and written language. Specifically in the projects that I will cover today, we're exploring ways to automatically assess cognitive health using verbal and nonverbal cues and automatically identify medical self-disclosure with the current emphasis on doing so in online forum posts. So I will spend the bulk of my time discussing my research group's work towards automatically monitoring cognitive health, since that project has been underway for a bit longer. And we've done this at 2 different levels of granularity. So we've looked at coarse-grained dementia detection, where we are classifying individuals as either having or not having Alzheimer's-related dementia. And then we've looked at finer-grained cognitive health prediction, where we are predicting a score ranging from 0 to 30, indicating an individual's cognitive health. Then I will close by introducing our newer work in identifying medical self-disclosure from online forum posts, and that includes the release of an extensive data set and corresponding benchmark models for the task. So starting out with our work on monitoring cognitive health, it is a really interesting problem to work on, and it's also highly relevant given the shifting age demographics that we're seeing in the US as well as globally. So by 2034, it is expected that the number of US adults over age 65 will outnumber the amount of US children under age 18. So with an aging population, you not only want to support physical health, you also want to support mental and cognitive health to make sure that people are able to maintain quality of life as they grow older. So one way to maintain cognitive health is to make sure that you catch age-related cognitive decline really early, so that you can quickly intervene with medication or lifestyle changes or some combination of those factors. However, cognitive assessment currently involves in-person cognitive tests with a healthcare provider, and that can be needlessly inconvenient for both the patient and the clinician, especially given our increasing shortage of trained healthcare professionals. So anything we can do using AI to reduce burden on healthcare workers while still maintaining appropriate levels of care is very welcome. And beyond that, in some cases, it may reduce stress for the patient. So some patients have physical impairments that make it difficult to make regular visits to doctors' offices. Some may live in geographically isolated areas, and some may just dislike going to the doctor's office for what they perceive to be non-emergencies, especially, for example, during times like these. So the question that we're trying to answer then is, what if we could ambiently and automatically assess cognitive health directly from patients' free speech in the comfort of their own homes, for example, through their interactions with virtual agents? So as already mentioned, we've tackled that problem at two different granularities so far. So we started out by looking at the problem of dementia classification. So basically trying to answer the coarse-grained question, does our patient have dementia or not? Then we moved on towards finer-grained approaches that seek to predict scores along a continuum based on the score range used for the MiniMental state examination, which is a really common cognitive test. And for both of these lines of work, we leveraged data from Dementia Bank, which is a collection of data sets containing audio files and corresponding text transcripts from interactions collected from patients and matched with their MMSE scores from in-person cognitive tests. So here's how I will be structuring today's talk. So we're at the beginning right now, discussing our work on monitoring cognitive health. So I just introduced the problem in general and provided some of its background motivation. And then in the next few sections, I will dive more deeply into different aspects of this process, including data collection, dementia detection, and MMSE score prediction. Then I will move towards a shorter discussion of our work on identifying medical self-disclosure. So I'll introduce that problem, describe the data set we've created for that task, and then go over the findings from our benchmarking experiments. And then finally, I'll close by discussing some intriguing future directions towards both research tasks that we're actively pursuing already or planning to pursue in the very near future. So the data that we have been working with thus far for all of our work on dementia detection has come from a source called Dementia Bank. Dementia Bank is a shared resource containing multiple corpora, and it's part of the larger TalkBank project. So TalkBank has spoken language data in a wide range of areas, including different clinical domains, child language, conversational language, and so on. So within Dementia Bank itself, there are recordings and transcripts of individuals with and without different forms of dementia, completing a variety of different language tasks in a variety of languages. So there's English data, of course, but there's also data in German, Mandarin, Spanish, and Taiwanese. So most NLP researchers interested in the task of dementia detection, including ourselves, have focused on one specific corpus within Dementia Bank, and that is known as the PIT corpus. So the PIT corpus contains audio recordings and transcripts from 4 different language tasks. So there is a picture description task, a verbal fluency task, a sentence construction task, and a story recall task. It was collected during a large longitudinal study in the 1980s, following individuals both with and without dementia. So overall, the data set contains speech from 104 control participants, 208 participants with dementia, and then 85 with unknown diagnoses. Individuals participating in the study were all elderly, and most tasks were completed only by individuals with dementia, but one of them, which is the picture description task, was completed by participants in both the control and dementia groups. So we focused on that picture description task, again, following prior work in this domain since data from participants both with and without dementia was available for that task. The picture description task in the PIC corpus was the cookie theft picture description task. So it's a well-known, scientifically validated standardized task where participants are shown an image, and you can see the image right here with a lot of different things going on in it, and they're asked to describe the image. So the descriptions provided by those with and without dementia tend to vary quite a bit in a number of ways, which is, of course, what we sought to make use of and encode in our models. So an interviewer engaged each participant in the cookie theft task and discussion, and they asked them to describe what was going on in the image. So the interviewer occasionally provided encouragement for the participant or clarification if they weren't sure what they were supposed to do, but they didn't directly provide hints or guidance towards specific conclusions. So these interviews were all audio recorded and then later transcribed using a transcription protocol called the chat protocol. So we're working directly with those transcripts in our work. And for our work on MMSE score prediction, we also explored features from the audio files themselves to a small extent. So an excerpt from one of the transcripts is provided here. The data samples in Dementia Bank are restricted to people or research groups for whom access has been granted. So I changed a little bit of the wording while still retaining the same core structure. I also removed the markers of nonverbal behaviors just to facilitate ease of reading. So this particular sample was from an individual with probable dementia. So then after the excerpt here ends, the participant proceeds to go on further with a description of the woman and then turns back to more elaboration regarding the children before concluding. So we used all samples present for the cookie theft task in our work on dementia classification. And a smaller subset of samples for our more recent work on MMSE score prediction. In total, the cookie theft data consists of 1,049 transcripts from the 208 individuals in the dementia group and 243 transcripts from the 104 individuals in the control group. So that makes the distribution fairly unbalanced, and that was something that that we and others have tried to address later on. Conversations with control participants tended to be slightly longer. So there were 97 words on average spoken by control participants, as opposed to 65 words on average by dementia participants, not including backtracking or other fillers like the word although these averages meant that overall the conversations were pretty short. So I've introduced the data that we're working with, and you have a basic understanding of the specific language task that we've been focusing on. So I'll move next toward a discussion of our approach for automated dementia detection, where we are distinguishing between individuals with and without dementia based on the linguistic patterns that are evident from their cookie theft picture descriptions. So for the task of automated dementia detection, we designed a neural network architecture that seeks to classify individuals into these two groups of individuals with and without dementia. And we designed it such that we could not only make use of implicitly learned sort of black box features, but also make use of engineered features that have been found useful in prior work. So the model accepts as input a full transcribed conversation, just like you saw a few slides ago. It processes it, and I will explain how the model works in the next slide, and then it outputs a binary class value indicating its dementia status prediction. So more specifically, Our model architecture is a modified CNN LSTM shown here. So many of you might already be familiar with neural network models, but for those who are not, a convolutional neural network or CNN and a long short-term memory network or LSTM are both neural network models. So CNNs are often used to find local patterns in images or more recently text that yield high predictive performance. And then LSTMs are often used for sequence processing. So situations where order is important, such as processing a sentence word by word. So we introduce a dense feed-forward neural network layer at the end of the model to facilitate the inclusion of manually engineered linguistic features considered significant by prior work on automated dementia detection. And that allowed us to leverage the power of a neural architecture without sacrificing the advantages of more targeted features in the process. So to address the class imbalance that was mentioned with respect to Dementia Bank, we added class weights to the loss function for the neural network during training. And then later on, during our evaluation, we experimented with versions of the architecture, both with and without class weights, as well as with and without the attention layer. In more specific detail, each input transcript was first pre-processed prior to being passed into the model to remove interviewer utterances and tokenize them into single word tokens. We removed interviewer utterances because our focus is on the participant. And additionally, if we learn to rely on the interviewer utterances as well, then it could be more difficult to transfer our work to settings where a chatbot had conducted the interview. So for each of the tokens resulting from the pre-processing step, we extracted a word embedding. For now, we've just used pre-trained glove embeddings. We also extracted a part of speech tag represented as a one-hot encoding. So then the word embedding and part of speech tag sequences were input to two separate but architecturally identical CNNs, and the outputs from those CNNs were flattened and passed into a bidirectional LSTM, optionally with the attention mechanism depending on the experimental condition at test time. So then we passed that output to the dense layer and a set of feature values extracted for the transcript as a whole. Using psycholinguistic and sentiment-based feature extractors were also passed into that dense layer. So then the final output is obtained from there. So the key advantage of that architecture was that it allowed us to take advantage, as previously mentioned, of both targeted and neural features. So then for the targeted features, these were data characteristics that prior work had suggested were well suited to dementia detection. And all of the targeted features we considered in our most recently published model are shown in the table here. So for our psycholinguistic features, we considered age of acquisition, concreteness, familiarity, and imageability. So age of acquisition is the age at which a particular word is usually learned. Concreteness is how tangible a word is. Familiarity is a measure of how often one might expect to encounter a particular word. And then imageability is very closely related to concreteness. So it's a measure of how easily a word can be visualized. So the psycholinguistic scores were all from the MRC psycholinguistic database. For our sentiment features, we considered the polarity of a given word, so how positive or negative it was, using a sentiment analysis tool available in a natural language processing package called NLTK. And then in addition to the psycholinguistic and sentiment-based features, we also looked at age and gender at the time of the visit, just to see if this was having an impact on performance. So for each of the psycholinguistic and sentiment features, we computed an average score across all tokens in the instance, which allowed us to compute a transcript level feature vector to be passed into the dense layer along with the transcript's neural representation. So for example, if we were computing our imageability score, we could take the tokenized transcript, which might look something like what you see here. We would go ahead and compute an imageability score for each individual word in the transcript that we were able to. We would average those values and then produce a single value to fill that slot in the feature vector. So we compared our approach to Carla et al.'s model. So that was a neural architecture that was fairly similar to ours, but without the inclusion of targeted features. And it was, at the time, it was the state of the art for the particular task. So we refer to that model as CLSPM throughout the remainder of these slides. So we randomly split our data set into 81% training, 9% validation, and 10% test data. And then we repeated that random shuffling 3 different times, reporting the average scores for each metric. We measured performance using a wide range of metrics, including accuracy, precision, recall, F1 measure, and area under the curve. And the raw number of true negatives, false positives, false negatives, and true positives achieved by each approach on the test set. So then we also compared several variations of both our model and CLSPM. So we considered a base case for each without an attention mechanism or any class weight correction, and then a variant for each that included an attention mechanism, and a variant for each with both attention and class weight correction. So that allowed us to measure the impact of these 2 components on the performance of the model as a whole. So our results are shown here. As is demonstrated, our model achieved state-of-the-art performance in accuracy, precision, recall, F1, and area under the curve by relative percentage increases of 5.2%, 7.1%, 4.9%, 2.6%, and 3.7% respectively. So with most metrics, our model achieved its highest performance when both attention and class weight correction were employed. So that was this condition right here. Class weight correction made a particularly noticeable difference in precision, both for our model and CLSPM. And our model's highest accuracy was 0.8820, and our highest F1 score was 0.9305. So beyond simply looking at the overall performance differences, we also performed a follow-up feature ablation study to facilitate further quantitative analysis. So we specifically looked at cases where we made changes to the set of targeted features. So in one case, we removed the psycholinguistic features, but retained all others. In another case, we removed the sentiment features, but retained all others. And then in this last case, we removed the demographic features, but retained all others. And the effects of this feature ablation were fairly minimal, as you can see. So that kind of suggests that the information provided by these 3 different groups is probably somewhat correlated. So the results are all here. Removing sentiment features resulted in slightly fewer true negatives and slightly more false positives, whereas removing psycholinguistic features resulted in small but somewhat meaningful drops in accuracy and precision. And especially with respect to precision, which dropped from 0.9312 in our model with all features down to 0.8870 when psycholinguistic features were removed. We also examined samples misclassified by our model to identify key distinctions among those groups, and found that generally misclassifications tended to occur when the speaker's linguistic style was more similar to that of the other group. So for example, false positives like the one shown here tended to include a lot of interjections like and oh, so those can be indicative of stalling behaviors. Whereas false negatives, like the one shown on the bottom, tended to be surprisingly clear, for an instance, from the dementia group. So then in addition to errors related to style, when looking and especially listening through misclassifications, we found that in general, important prosodic distinctions between the two classes seemed to go largely unnoticed. So these might be more effectively encoded using audio features. We didn't explore audio features in this work, but we do to a small extent in the work on MMSE score prediction. So overall, in our analyses, we demonstrated that the inclusion of our targeted features led to a measurable performance improvement relative to the existing CLSTM state-of-the-art, demonstrating that implicitly learned features still miss some important semantic patterns indicative of dementia status. The importance of conversational patterns in general is further supported by the fact that for both CLSTM and our approach, the introduction of an attention mechanism, which allowed better focus on those patterns, led to higher performance. And then the benefits of adding class weights to the model's loss function were less clear. The class imbalance in Dementia Bank is a well-known issue among researchers working on problems in this domain, but unfortunately it still hasn't really been addressed that much. So the key takeaways from this first part of the work are that we introduced a neural dementia detection architecture that allowed us to leverage both deep learning techniques and engineered features. And we found that this model outperformed the state of the art, which didn't make use of the engineered features. Our source code is publicly available online, so you can download it and play around with it yourself at the link provided here. Going forward from this work, we're planning to explore additional targeted features for the task, as well as some audio-based features. We're also interested in interpreting the neural features that were implicitly learned by our model in order to understand what types of latent characteristics they're capturing in the Dementia Bank transcripts, and perhaps provide some interesting clinical insight. So let's see, it looks like there's a question in the chat. Oh, yeah, so someone in the chat asked, do I know if Google Health, Microsoft, or Amazon are using this database? So that's a good question. I don't know if they are. I think they probably could not use it in commercial applications just because of the data use agreement that I know academics have to sign for using it. So I think, due to patient privacy, it might not be used. Oh, is there another question?
I don't think so. Please go ahead.
Okay. Yeah. So yeah, I think I would be a bit surprised if they're using this database just because of like the patient privacy and data use agreement and stuff, but they probably have similar types of databases that, are maybe proprietary to them, but that probably are fairly similar. So let's see. And yeah, anyone can feel free to jump in with questions at any time. I'm happy to answer any questions that come up. But yeah, so that was the work on automated dementia detection. So we saw that engineered features can provide useful support to neural models for the task, and overall our model achieved state-of-the-art performance. So from there, we moved on to the more fine-grained task of automated MMSE score prediction. Oh, there's another question. So that's a very good question. So what I would like to ultimately see with these tools, so someone asked what will be the future of cognitive diagnosis using these tools. So I wouldn't want tools like this to replace a doctor. I think it's important that there's still a human in the loop somewhere checking things out. But what I would like to see eventually would be tools like this being embedded to some extent in everyday applications, and that way you could potentially pick up on things a lot earlier. So maybe someone isn't, going to a doctor because they haven't really noticed any changes in their own speech patterns or anything, or in the way that they're interacting with the world, but maybe a computer could pick up on that and kind of give them a little warning and be like, hey, you might want to go check this out. So maybe people could get into the doctor earlier on. So that would be where I would envision this being really useful, not as like a replacement for doctors, but as something to support them. Yeah, and so the accuracy of part of speech tagging, that's a really good question too. So a lot of the sentences are very like conversational, and part of speech taggers do struggle more definitely when they're working with input like that rather than like the nice edited text that you see in a book. And so I can't remember off the top of my head exactly what the accuracy of our part of speech tagger was. I don't remember being overly concerned about it, but I can look into that and get back to you, because that is a good question. There are part of speech tagging tools that are developed more for conversational speech, but it is definitely harder to get accurate part of speech tags for messy, like noisy inputs. Let's see, so one more question or several more. So suppose you have a police or essential worker and need to know if they're fine to do their work. Yeah, that could be a good use case for something like this. Yeah, and in many cases that might so what we're looking at right now in this particular work is dementia detection, but more generally having some kind of tool that checked for general well-being could be very useful for situations like with police or essential workers. So that could be an interesting application as well. That's not something I have explored personally, but I think there could be like very good real world implications for that. And then another question. So I mentioned speech and sound as input. What about video? Yes, so I have a whole other line of research that I'm not covering today, but that deals with multimodal natural language processing, particularly incorporating both visual and linguistic features. In this particular case, the data set we were working with just didn't have video, and so we couldn't use it here. But I do think that facial expressions and other visual cues could be very informative. In general, working with video increases the compute resources needed. And so that could be potentially a concern if you wanted to embed something in an app, I guess. But depending on the application you are working with, I do think that facial expressions and stuff could be very useful for this task. I think that there isn't a great data set out there right now with that information, but if one becomes available with video recordings, I think a lot of people would be interested in that. Okay, so I'll move on to So the work I was just talking about was covering dementia detection. So classifying, does someone have dementia or not? We also did some work that looked at this problem from a more fine-grained perspective. So we predicted MiniMental state exam scores. So the MiniMental state exam, or MMSE, is a clinically validated assessment that measures cognitive status in a variety of different areas. So the scores range from 0 to 30, where higher scores indicate that the person has higher cognitive health, and lower scores indicate that the person has more severe forms of dementia. So this is what the MiniMental state exam looks like. So the questions correspond to simple tasks that individuals without cognitive impairment should be able to perform or recall easily, but the individuals with cognitive impairment tend to find much more challenging. So for example, questions about the time and location, questions instructing the person to remember short sequences or perform simple calculations and so forth. So we conducted our work on MMSE score prediction in the context of a challenge at the Interspeech conference called the Address Challenge. And so we were trying to answer the 3 questions that you can see here. Looking at how discourse characteristics contribute to predicting MMSE score, looking at how the performance of acoustic features compares to text-based features for the task, and then looking at, in general, which features and patterns are most beneficial for it. And so we were curious whether the answers to some of those questions would be similar to what we found with dementia detection, or different, given that this was a more fine-grained regression task. Since we completed this work in the context of the Address Challenge, we trained and evaluated our model using the challenge training and test sets. So it was a subset of the PIT corpus that was used for the dementia classification work. So basically this subset was gender and age balanced. Approximately even numbers of male and female participants in both categories, and kind of balanced across ages as well. So the instances themselves remain the same as already described. So they were audio recordings and then the corresponding text transcripts for participants completing the cookie theft picture description task. And so then in addition to the full interview audio recordings, the challenge data set contained sequences of short audio clips for each transcript, segmented for voice activity of 10 seconds maximum. So that information was provided as well. Our data set was even more limited than the one we were using with dementia classification, since in balancing age and gender, that necessarily meant that the corpus became even a little bit smaller. So our focus in this work was on feature exploration rather than the modeling architecture itself. Typically, neural models require many more samples for training. We also, in this work, in contrast to our earlier work, made use of both the transcripts and the audio files. And specifically, we used the pre-segmented short clips. Once again, we removed interviewer utterances from the transcripts. We also removed non-alphabetic characters. So things like specific numbers, for example. And then we formatted the input for a given transcript as a sequence of sentences. And then we pre-processed the short audio clips by setting each segment's log energy threshold to 65 decibels. So that's generally the upper bound for noise level in like a normal conversation or laughter. And we formatted that input for a given conversation as a sequence of pre-segmented, like approximately 10-second audio clips. So then we extracted a variety of text-based and acoustic features for our work, and that allowed us to explore the impacts of a variety of different types of information. So we looked at 4 broad groups of features. So lexicosyntactic features, psycholinguistic features, discourse-based features, and acoustic features. And you can see the specific information that we use for each of those feature categories here. I won't describe them in depth because I know we're a little bit behind on time, but there's a lot more information in the paper about it as well. So then we were doing this in the context of the address challenge. So we were allowed 5 entries. So we selected the following subsets of features based on preliminary cross-validation experiments, as well as for their diversity. So these feature subsets, along with one neural condition, which was partially a sanity check to make sure we weren't completely off base and focusing on engineered features, explore a wide range of different data characteristics. So for the neural network condition, we used a neural language model called Distilbert. So Distilbert is a popular variation of a transformer-based language model called BERT that is used in a lot of NLP tasks. So the Distilbert tokenizer processes the input, and then it processes unseen tokens as subword units. So it's able to make use of, for example, the discourse tags in our transcripts and other vocabulary that wasn't present in the original training corpus. So it encodes the tokenized input, it passes the encoded representation to the final fully connected network. And then that applies linear transformations to the data that ultimately predict a single output neuron representing the MMSE score for the patient. So in preliminary experiments, again, using leave one out cross-validation on the training set, we looked at both support vector and Gaussian process regression models for all of the feature-based conditions. We found that support vector regression worked better, so we used it for our challenge submissions, with the one exception, of course, being the Distilbert condition. For the models that considered text-based features, we made predictions at the transcript level. And for the model considering acoustic features, we employed a segment-based regression model following the existing acoustic performance benchmark, finding that an overall transcript level score could be used by averaging the individual regression outcomes. So this is what that segment-based regression model looked like, assuming that there were in different acoustic segments. Each segment was individually fed into the trained regression model, and an output MMSE score was predicted. So those in predicted MMSE scores were then fed into an averaging function, and a single output MMSE score was produced from that. So the MMSE predictions for this challenge were evaluated using root mean squared error, with the equations shown on the left here, using y hat for the predicted MMSE score and y for the patient's actual MMSE score. And we achieved the results that you see on the in the table on the right. So as you can see, selected feature resulted in the highest performance with a root mean squared error of 4.34. So that was a 16.5% decrease from the existing linguistic benchmark on the same test set. So a considerable improvement. All acoustic was the lowest performing model, but it did still achieve a significant decrease from the existing acoustic benchmark on the same test set. But overall, these results pretty clearly demonstrate that text-based features outperform acoustic features for this task, and moreover, that well-selected engineered features still do outperform neural features for the task. So then, when examining the features included in the selected features subset, we found that a variety of different text-based features contributed most to the condition's performance. So in particular, non-content words and discourse connectives were found to be highly informative, as were some discourse-based count features. So we also qualitatively compared samples from individuals with high and low MMSE scores, and we found that those with higher scores in general created longer descriptions and used more content words and complex phrases, whereas those with lower scores used shorter descriptions and more pauses and filler words. So that suggests that verbal disfluency markers could be important indicators of cognitive status. And then finally, we analyzed trends in RMSE scores across the binned MMSE score groups, and we found that the model's predictive power was best with high MMSE scores. So that is likely an artifact of the training set distribution. So there were more samples from people with high MMSE scores than lower ones. So on the right over here, we have the binned MMSE scores. We have the corresponding RMSE scores. So the left y-axis has frequency counts, and the RMSE scores are on the right y-axis. So then these percentages above the histogram bars indicate the training set frequency for those MMSE bins for reference. So the key takeaways for that segment of the work are that the text-based features are more informative than the acoustic features for MMSE score prediction, which is an interesting and somewhat surprising result because of the limited body of work until now that focused on acoustic features for MMSE score prediction. We also found that nonverbal discourse tags contribute substantially to model performance. So that suggests that a worthwhile future direction would be to explore more informative features in this area. So one idea worth pursuing may be to develop mechanisms for extracting these automatically from the normalized speech signal, since one limitation of the current work is that it relies on existing discourse tags included in Dementia Bank, so that makes it difficult to scale to potentially larger data sets or real-world applications. Let's see, okay, so there's a few more questions in the chat. Yeah, so we used machine learning. So someone was asking how to assure that there is no bias. That's a very good question, because especially when you're dealing with clinical predictions, you don't want to make any biased mistakes. So, I can't 100% say that there's no bias in the data, and that's why I think that this should not replace a doctor. It should be used more as a support tool. I do think with the data set that we used for MMSE score prediction, that was a data set that was age and gender balanced. And so, there was an effort to reduce bias by training on balanced data. But in general, bias is like a hugely important topic right now in all aspects of machine learning. And so I think it is important to continue to validate that models like this are not making biased decisions in any way. Another person asks, how did you compute the importance scores? So we used mean decrease in purity from a random forest classification model in order to determine the importance of different features for this model. Yeah, so it looks like the other question was about that as well. Yeah, so basically the feature importance was learned using a random forest based model. Okay, so in the final part, I'll try to be very quick with this final portion of the talk. So I'll talk now about a newer project that my group has worked on where we're identifying medical self-disclosure in online forum posts. So medical self-disclosure is basically the act of voluntarily revealing information regarding personal health details that are relevant to understanding or diagnosing or treating various health concerns. So it's a critical part of patient care because if people don't disclose, you know, how they're feeling, what is happening to them, it's really difficult to come up with a treatment plan. But it's also a really tricky part of patient care because especially in, you know, more sensitive scenarios, people may be hesitant to divulge certain details in face-to-face interactions. So studies have shown that people are likelier to disclose relevant health information online rather than in face-to-face interactions. You know, even though when they do this online, they're oftentimes just talking to people without medical expertise. So that might be because in online settings, people can more easily avoid discomfort or kind of hide in a way if they're dealing with sensitive topics. So we eventually hope that patients' inclinations to self-disclose online can transfer to a general inclination to self-disclose to a computer or virtual agent, and that these disclosures can in turn be used to supplement clinicians' records from their in-person encounters. So then that could help lead to quicker diagnosis and enhanced understanding of patients' healthcare issues. So before doing that, of course, we needed a data set for the task. So part of this work thus far has centered on constructing a large relevant data set. So, you know, although some prior work has explored self-disclosure detection in general, no work has focused on medical self-disclosure specifically. So we acquired manual self-disclosure annotations from pre-trained annotators for thousands of randomly selected social media and online forum posts. So you can see a couple examples here. So the annotators initially labeled each post on a scale from 0 to 5, where 5 indicated high self-disclosure and 0 indicated no self-disclosure. We eventually ended up averaging and adjudicating those scores and converting it into 3 discrete classes. So we have a no self-disclosure class, a possible self-disclosure class, and a clear self-disclosure class. So overall in the data set, we collected and labeled 6,639 posts. Those are distributed across 3 classes that you see here. So the possible self-disclosure class was less frequent, and we also had slightly lower inter-annotator agreement for that particular class. So, you know, humans have trouble identifying possible self-disclosure as well. So that ended up being the most challenging class for our model to learn also. We're currently in the process of expanding this data set by a few more thousand posts, hoping to get the distribution a little bit more even. I don't have those numbers up yet because we haven't fully validated the annotations yet, but I believe that we do have a slightly more even distribution in the updated version of the data set. So we created the data set and then we used it to train a suite of classification models. So we examined both classical and neural machine learning models. So you can see the different models and architectures here. For the classical models, we used TF-IDF vectors for our input features with the vocabulary of the 5,000 most frequent words in the training set. And to represent our input for the neural models, we used 100 dimensional glove embeddings, and those were pre-trained on Wikipedia and GigaWord. We also looked at two different experimental settings. So in the easier condition, we looked at binary classification just between no self-disclosure and clear self-disclosure. So we removed the kind of messier possible self-disclosure cases. And then in the other setting, we did include those. So this was a multinomial classification. So we predicted either no self-disclosure, possible self-disclosure, or clear self-disclosure. So we unsurprisingly found that classification models were able to learn the binary task more easily, and they demonstrated impressively high performance. So this was the best performing model for both our binary and multi-class conditions. So you can see the multi-class model still did achieve high performance though. So that does provide a strong performance benchmark for future work. This slide shows how all of the classification models did for the multi-class classification setting. So in general, neural models outperformed traditional classification models, which is fairly typical in machine learning tasks, but good to confirm because in other health-related tasks, including the one we just saw with MMSE score prediction, that was not the case. I don't have a slide showing it, but when the performance was broken down further, it was the possible self-disclosure class that was struggling the most. So the classifier had the lowest performance with that particular class. So it looks like humans and machines are kind of struggling with the same thing in this case. So then finally, we compared to a top performing model for general self-disclosure detection. So not medical, but just any kind of self-disclosure to tease apart the extent to which medical and general self-disclosure were separate problems, with the assumption being that with sufficient overlap in language style and other properties of self-disclosure, a general model might work reasonably well. So we compared our top performing model with the general self-disclosure model and then a most frequent class baseline as kind of the performance floor. And we found that our model performed significantly better than the general self-disclosure model. So that does help establish that medical self-disclosure is a distinct task that relies upon separate patterns and nuances from detecting other forms of self-disclosure. In addition to the quantitative results, we looked more qualitatively at the data. So these were the words that were most closely correlated with each of the self-disclosure classes using a method called log odds ratio with an informative Dirichlet prior. And so you can see that with the clear self-disclosure class, there are a lot of first-person pronouns and objective terms that may be indicative of specific symptoms or measurements, maybe medications or treatments. Words associated with possible self-disclosure are more subjective and a little bit emotionally charged. And then words closely associated with no self-disclosure tend to be second-person pronouns or maybe first-person plurals. So words that might be more associated with support or acknowledgement of someone else's disclosure. So then the key takeaway from this branch of the work is that we established that identifying medical self-disclosure is novel and challenging, so that provides motivation for additional follow-up work in this area. In our experiments using a fairly large data set, we found that neural models outperform manually engineered feature-based models for this particular task. And then we also found that the different categories in our data set have distinct linguistic patterns associated with them. So those are the three kind of branches of work I was covering. I know that we are short on time, so I won't spend too much time. I just have a couple more slides talking about where we go from here, but I'm happy to talk about that with people afterward as well. But basically, there are a lot of different interesting directions that we would like to pursue. So currently, we've looked only at English language samples, but of course, people have cognitive health problems all over the world. They don't all speak English, and so we would like to experiment with cross-lingual transfer to see if we can achieve similar task performance on non-English samples. We'd like to explore topical features for dementia detection, specifically with this picture description task, because there are certain components of the picture that in, psychologically normed studies have been important, that we could potentially identify, discussions about using topic modeling. We'd like to investigate transfer to other language-based tasks. So can we predict dementia, not only in the context of picture description, but in the context of general conversational speech? And then develop frameworks for collecting data. So can we build chatbots that are well suited to eliciting the kind of information we need to identify cognitive health concerns? For medical self-disclosure, similarly, we'd like to develop frameworks for eliciting medical disclosures. So can we build chatbots that encourage the kind of disclosure that we see in online health forums? And then can we reliably identify medical self-disclosures and distinguish them from general patient utterances when engaging with a chatbot? So that was a really quick overview of the work I'm interested in pursuing. That overall summarizes where we are right now. There are a lot of topics that I'm really excited about pursuing in the future with this work. This was a team effort with a great group of grad students who are listed here. So yeah, let me know if you have any questions. I'd be happy to answer them here or via email or whatever method you would like to discuss it. And that's all.
All right, thank you so much for the wonderful talk. And thanks everyone for those questions as well. I don't know, Natalie, do you have a few minutes? There are two more questions.
Yeah, sure. Yeah, let me check the chat.
I can read it out.
Okay, sure.
So, excuse me. Is this all language agnostic, or does the process account for patient's assessment based off second, third languages?
Yeah, so that's a very good question. So the current data set that we've been working with, all of the participants in that data set were native English speakers, and they are using English in the data set. So there could definitely be differences in how second language speakers were scored by these models, and that's something that we just don't know yet because we don't have the data. One of the directions that my group is really interested in is exploring cross-lingual models. So seeing if we can transfer what we've done with this work on English language data to other languages as well. So within Dementia Bank, there are subsets of the corpus in like Mandarin and German and a few other languages. And so that is a direction that we are interested in pursuing, to look more at like how this works with non-English data and with speakers of other languages.
I guess that answers the next one as well. The question is, can we contribute in other languages, Spanish, for example?
Oh, okay, yeah. So I see someone says, yes, share contact details. So yes, please contact me at the email address here, or if you want to read papers about some of this work, I have them listed on my website. And I'd also be happy to connect people with the grad students who have been working on these projects.
Any other questions? I have one. This is more applied. So do you have any collaborators who are doctors or in the healthcare sector that's actually trying some of these on the other end?
I do have some collaborators on the dementia detection work. So I have some collaborators who are clinicians at an Alzheimer's disease research center. And so they are actually in the process of collecting data that we're hoping to use to explore one of the other kind of aims I have in upcoming work. So they're collecting conversational data from elderly individuals with and without dementia. And so these people are not completing the picture description task. They are actually like recalling an important event from their 20s and just talking about it for 5 to 10 minutes. So we're working with them, and they are helping refine what things we should look for from the clinical side. So answering some of the questions we have that we don't know the answers to because we're not medical doctors. And so that has been a fun collaboration. That's a fairly new collaboration. But yeah, we've been working with them to help identify what are the specific questions we should be answering, and then can we apply these methods that we have built using picture description task data to more general conversational language.
Thank you. Any other questions? Okay, thank you so much. Thanks again for the talk and taking all the questions and staying a few minutes over a few minutes past 2.
Yeah, it was really fun visiting like virtually, and I would love to visit in person sometime as well.
Yeah, would really be great to have you here and meet some of our faculty and graduate students. So we'll definitely plan on that when the campus gets a little bit more busier.
Yeah.
Thank you for the talk. It was great.
Thank you very much.
Good stuff.
Love it.
Muchas gracias.
Thanks.
Thank you all. Bye.
Bye.